Welcome back, guys. Let's talk about solving equations that already have radicals in them. In other words, radical equations is what they're usually called. Not the cool kind from California though, right? Not radical equation. So, notice this is a radical equation. It starts off with the square root, right? So we need to think about what have we been seeing this whole time we've been dealing with radicals that could possibly undo a radical without actually having to perform it. I want to do the opposite of it, right? Remember, radicals are often the opposites of powers, as long as the power and the root number match. And a square root is the same thing as a 2 root. So I would need a 2 power, or in other words, squared, right? So in here, I'm going to start by squaring both sides. Okay? So in this case, since the square is directly acting on the square root, I'm basically doing the opposite of that. It's going to go away. So I'm left with just 3x minus 2. And then on the other side, 4 squared is 16. Once I'm to this point, it's just a plain old linear equation. Now it's to the point of, let's get x by itself. Yeah. So I would add 2. 3x equals 18, and I would divide by 3, which would land me to x equals 6. Okay, now before I move on to the next example though, I want to demonstrate to you something that's slightly different and makes these equations feel like they're about a half step up from some of the other equations that we've talked about. Let me show you an equation that's almost identical to this one. What if it were the square root of 3x minus 2 is equal to negative 4? Right? Almost identical, but different by that one sign. Right? So here, my first step, just like last one, is that I would square both sides. But when I'm squaring both sides, don't forget that's an entire side that has to be squared all together. So the negative and the 4 get squared together. Notice where that lands me is the same place that we were in the last equation, which is here. Okay? And in any time in math, you'll find that things that get rid of negatives, we call them even operations, will have this sort of effect on equations, right? They sort of have this duality. I would then solve this the same way, and notice I would get the same answer, of course, because it's the same linear equation in the second step. Okay, great. So that means they both have the same answer. No, they don't. Remember, what a solution actually is a value that I can substitute back into the original equation, and it should cause a true statement. Okay? So let's do that here for both of these guys. Okay? On the left here, if I plug 6 back in, I'm going to have square root of 18 minus 2 is equal to 4. Because 3 times 6 is 18, right? Then I would have square root of 16 equals 4. And I would have 4 equals 4, which makes this solution very, very good. All right? Let's do the same thing with the other equation here. If I were to substitute the 6 back in, right, I would have the square root of 18 minus 2 equals negative 4. Sorry about that. The square root of 18 minus 2 equals negative 4, which would give me square root of 16 equals negative 4. And I know what you're thinking, right? Negative 4 could be a square root of 16 because negative 4 times negative 4 is 16. But that's not the way square root is defined. Here, there is no negative sign in front of this square root. And the square root already is there. It's predefined. Just like in your calculator, if you punch in square root of 16, you're going to get positive 4, not negative 4. Because of the way humans have had to make the decision about the definition of those kind of operations, this is going to be a false statement because of that, which of course then means that this is a false solution which, since that was my only solution to begin with, that means this equation has no solution. Okay? Now that's not always what's going to happen. Sometimes you'll have multiple solutions to choose from, and maybe only one of them will work, and other kind of mixtures like that. But these are very straightforward equations, right, with just the one variable and a few operations. So you've got one or none in these simple cases here. Okay? And it's because of the way square root interacts with negatives. Here's the thing, though. When you're approaching one of these equations, you may not notice, or you may not have the ability to notice, like they may be too complicated for anybody to notice, that the solution's going to come out bad no matter what, right? Since you have no way of knowing beforehand, you're still going to work through the equation, right? And then you're going to want to check. So a little asterisk, put it in your notes next to radical equations, right? Radical equations are a must-check type of equation. They're just that half step more complicated that when you're solving them, you want to check them every time. Not because you may have gotten a step wrong somewhere in there, but because the solution that you've gotten to, no matter how correct it feels, does not actually act as a solution, right? Radical equations are must check. Okay? Let's do the next example down here. Third root of x minus 5 plus 2 equals 1. All right. So this is sort of the next tier up. I don't have the radical by itself like we did in the other equations. This plus 2 is not part of the radical, and that could cause a mess if I were using exponents on that, because remember, exponents don't distribute over addition. So he's got to go. I'm going to subtract the 2. That's going to leave me with the cube root of x minus 5 is equal to negative 1. Okay, fine. Now I've got the same structure of equation as the ones up there. So I'm going to want to do a power. That's the opposite of the root number. Instead of square root, now we've got third root. So I'll do third power. But I've got to do that to both sides. So third power. Where does that land me? Well, these two are opposites. I can immediately get rid of them. X minus 5 equals negative 1 to the third power. Negative 1 times negative 1 times negative 1 is negative 1. And I want to solve for x. So I'll add 5. Okay, well, that's going to tell me that x is 4. Right? Don't forget, must check, right? So I'm going to take x equals 4, plug it back into the original. Third root, 4 minus 5 plus 2 is 1. Third root of negative 1 is negative 1. And negative 1 plus 2 is 1. So this is a good solution. Okay? So x equals 4 is a good solution for that one. Linear equations. Both of these are going to cause me to have some sort of quadratic instead. And we've talked about how to solve those, remember, with factoring. So they'll be slightly different in the process here, only because of the latter steps. Let's take a look. First, just like last time, I want to have that radical isolated so that when I use my power, I don't have to do something complicated if I don't have to, right? So I'm going to start by adding the 2x to both sides. By adding 2x plus 0, I just get 2x. Okay, so then I have the square root. I want to get rid of it. So I'm going to square both sides. Be careful. You're squaring the entire side there. All right, so then the square and the square root are going to wipe out. leaving me 9x minus 2 is equal to 4x squared. Okay. Then I notice it's a quadratic, right? Because of the x squared, and nothing's going to add it away or make it not a quadratic. So then my next thought is, wait, if this is a quadratic, all of my methods say that I've got to have an equal 0, right? If you're factoring or using what we call the quadratic formula, right? You need an equal 0. So I'll go there next. I'm going to have to subtract the 9x, right? Subtract the 9x. And I'm going to have to add the 2. When I do those, I'm going to end up with nothing on the left-hand side, and there's my 0. And I did move to the right on purpose because I do want my highest term, my squared term, to be positive here, right? Okay. So then from here, you're going to want to factor it whatever way you're most comfortable factoring. I prefer the AC method, right? The 4 times 2 is 8. And then I think of two numbers that multiply to 8, which also add to negative 9. In this case, those two numbers would be negative 8 and negative 1, right? Okay, so then from here, in my method, the way I do it is I just copy the 4x in front of each one, and then I look for extra things that I can GCF out and throw away. In this case, 4 and 8 have a common 4, so that's the one that I'm going to factor and throw out, leaving me x minus 2 times 4x minus 1. And then from here, remember in our solving method, if it's multiplied and equal to 0, I can split them and solve them. Here I'm going to get x equals 2, and here I'm going to get x equals 1/4, right? Because I would add 2 to solve that one, and here I would add 1 and divide by 4. So I have my two solutions here. But wait, don't forget, we're in a radical equation situation. So I've got to check my answers to see if one, both, or none of them work. We have to check them, right? It's a must-check type of equation. Okay, so here I go. I'm going to start by checking the x equals 2. So square root of 9 times 2 is 18, minus 2. And then minus 2 times 2, which is 4. I'll go ahead and just write that in there. Right? 9 times 2 and 2 times 2. So 18 minus 2, square root of 16. 4 minus 4 is 0. So 0 equals 0. That works out. So x equals 2 is a good answer. Does that automatically mean that x equals 1/4 is not a good answer? No. There are occasions when both solutions can work. So I've got to check the other one. Got to. Okay, so here we go. I've got square root of 9 times 1/4, 9/4, minus 2. And then minus 2 times 1/4, 2/4, which is 1/2. Okay, from here, instead of 2, I'm choosing to write 8 over 4. 8 divided by 4 is still 2, but they have a common denominator. So that leads me to square root of 1/4 minus 1/2 is 0. And the square root of 1/4 I can split into square root of 1 and square root of 4, which gives me 1/2 minus 1/2 is 0. In this case, notice I get 0 equals 0, which works out fine. And therefore the x equals 1/4 is also a good solution. It can happen sometimes that both of them work out. And then other times maybe only one of them, and sometimes neither of them. You have to check these. You just never know. Okay, so let's move down to this one. Square root of 9 plus x equals x plus 3. Okay, so I notice my radical is already isolated. I'm going to square both sides. Remember, the whole side. I cannot distribute a power over addition, so I have to square the whole thing. Okay? And what that means is I'm going to have to write it twice and multiply it out. Some people call it FOIL, some people call it multiply everything to everything, or big distributive, or whatever, right? I've got to multiply that out. Okay? So that leaves me with 9 plus x is equal to x squared plus 6x plus 9. Okay? Right? Because I've got x squared, 3x, 6x, and 3 times 3 is 9. And again, I notice it's a quadratic. Remember what that means? I need equals 0 in order to have any of my quadratic methods come out the way I want to. So I'm going to have to subtract an x and subtract a 9. So here I get 0 is equal to x squared, and then I've got plus 5x, and then these zero out. So that leaves me with x squared plus 5x. Okay, so we're solving by factoring. This one doesn't need any complicated factoring method. It just needs a GCF. I'm going to factor a common x out, leaving me with x times x plus 5. And just like earlier, when I have a multiplication and it's equal to 0, I can split it. This tells me that either x is 0 or x is negative 5. Okay? Now again, don't forget, we must check these, right? Radical equation must check. So here I go. I'm going to check the x equals 0 one first. Square root of 9 plus 0 equals 0 plus 3. Okay, so square root of 9 is 3. 0 plus 3 is 3. So 0 works. All right. Next, let's check negative 5. So square root of 9 minus 5 is square root of 4. And negative 5 plus 3 is negative 2. Okay, so then what I've got is 2 equals negative 2. Uh-oh, those aren't equal anymore, right? So this is a bad answer. Negative 5 cannot be used as a solution to this equation. So in that case, only one of them worked out. All right, one more example, guys. Talk about one of these equations that has more than one radical in it. In the case of having more than one square root like this, it's more of a divide and conquer, pun intended. I'm going to want to split those guys up. I don't want them on the same side if you have the choice. And that is because when I do my power, I won't be able to distribute it. But what I can do is focus on one radical at a time instead and get rid of them that way. So in this case, the more complicated radical is this guy, the square root of the 3x plus 1. Okay? So what I'm going to do is I'm going to focus on him first since he's more complicated. And the way I do that is by subtracting this radical so that he's no longer on this side. Okay? But of course that means I'm going to have to subtract it over here. So what does that get me? It gets me to square root 3x plus 1 is equal to 2 minus the square root of 3x. Okay? Now I'm going to get rid of this radical. I'm going to square. But of course I have to do that to both sides, and I have to do it to the entire side. Here's the drawback now. Maybe you're already seeing it. I'm having to square a parenthetical whole object that has a radical in it. I'm going to have to write that thing twice and multiply it out, right? Some people call it FOIL, some people call it super distributive property, whatever. Okay? I'm going to have to multiply that out. So my left-hand side is still 3x plus 1 now because of the nice little opposites that we have there. And on this side, I'm multiplying out 2 minus square root of 3x times 2 minus square root of 3x. All right, so let's do that multiplication. I've got equals 2 times 2, 2 times negative square root of 3x, so that's negative 2 square root of 3x. 2 times negative square root of 3x is negative 2 square root of 3x. And then negative times negative is positive. Square root of 3x times square root of 3x. We've seen that before in the rationalizing lecture, right? Whenever you multiply two radicals that are, square roots specifically, two of them, you end up with that same object back, just the object. So 3x in this case, right? Also, don't get this confused with the conjugates. They're not conjugates. They're the same sign. So these two pieces in the middle are not going to add out to 0. They will, however, combine, right? I will be able to combine those in this next step. Okay, so let's see what we get. I have 3x plus 1 is equal to 4 minus 4 square root of 3x plus 3x, right? So I'm able to combine those there. All right, well, I got rid of one of the radicals. That's what happened. One of the radicals is now gone. Sure, it looks a little bit more complicated just because there's more pieces, but it's actually not, right? I now only have one radical. So I'm going to focus on him next. I'm going to focus on this radical here, and I'm going to try and just get that one by itself. Because once I get a radical by itself, remember, I can use exponents to get rid of them. Okay, so that means I'm going to subtract this 4 here to get it out of the way. That's a minus 4. And I'm going to subtract this 3x here, which is going to subtract here. Actually, that works out quite nice, doesn't it? All right. So then in the next step, I've got 1 minus 4 is negative 3. And it's equal to negative 4 square root of 3x. And I want the radical by itself, right? Okay. So let's do that. I'm going to divide both sides by negative 4. So now I've got 3/4 is equal to square root of 3x. There's that square root by itself. What am I going to do? I'm going to square, right? I'm going to square both sides now. That's going to end up with 9/16 is equal to 3x. But I want x, not 3x. So I'm going to divide by 3. And when I divide by 3, since this is already a fraction, I'm going to multiply by 1/3 to be the same action, the equivalent action here. And this is actually going to allow me, in this case, to reduce 9/3. And so the answer I end up with is 3/16 is equal to x. Okay, let's check that answer. Right, because we're in a square root situation, we got to check it. Let's do that. So I'm going to take the 3/16 and I'm going to plug it back into the original equation. So square root of 3 times 3/16 plus 1 plus square root 3 times 3/16 should equal 2. Okay, 3 times 3/16 is 9/16. And instead of putting 1 here, I'm going to put 16/16. Okay, so let's continue with just this piece for a moment. That's going to give me 25/16. And I can do both of those, right? Square root of 25, square root of 16. That's 5/4. Okay, let's do the next one. 3 times 3/16, 9/16. I can do both of those square roots, right? That's going to give me 3/4. Okay. Well, 5/4 plus 3/4, that's 8/4. And 8 divided by 4 is 2. So you'll notice 3/16 is a good answer. Okay. I hope this helps in your endeavors to solve radical equations.